hello there. Moving on to Chapter 3 of our S650 Tuning 101 series. Today we're going to be looking at valve trains, what they are, what they do, all the fun stuff related to this component. We're going to be getting into what is a valve train components, the camshaft and cylinder heads, intake and exhaust valves. We're going to be looking at some of the very specific S650 twin independent variable camshaft timings that are made possible by the individual camshafts, right? When we're getting into why there are two of these, right, total, which is a little different from other engines. And we're also going to be looking at the angles and phasers and all the different ways we can control the camshafts to change all sorts of functioning aspects of the engine. We're also going to look at some of the common modifications that happen with valve trains. So, really kind of neat stuff. Let's get into it. What is a valve train? So the valve train, it completes the engine assembly. It's a large assembly that fits on top of the cylinder heads. There's two of them, and it directly mates on, and it transforms that core short block, which is just the block itself, the crankshaft, the cylinder heads, right? Everything we looked at, cylinder heads, apologies, the pistons and rods, everything we looked at last time, and it changes that smaller assembly into the long block, which is essentially a completed engine. Throw on a transmission, and suddenly you've got a complete powertrain. Right, so that's how these things all add up and keep building on themselves. The valve train has a very critical job. This is the component that controls the engine's breathing, both the input and the exhaust. Last time we looked at how there was the intake manifold with its runners, and there's the exhaust system, right? I collected the headers and the collector and all that. Those are the pathways for the airflow, but the actual precise window, the little moments where air is coming into the cylinder and going out, next time we're going to look at the four-stroke power cycle. This is all controlled by the valve train. So like I was just saying, yeah, the intake manifold and the headers, they make it available, but it's the valves that actually control these moments. And if you think about it like how we breathe, right? You know, we use our nose, our mouth, our throat to actually control exactly how the air comes and goes. The very way I'm speaking, right, and choosing to use very precise movements with my voice box and getting, the air in and out to make sense, to make language, all that good stuff, right? The valving mechanism is what's controlling those precise motions, right? So this is what we're going to get into today. This is critically important, excuse me, because different aspects of engine performance are dramatically affected by this airflow, and you'll see, right, as we continue. Let's move through to the material here, be a little less mysterious. Okay, components. Let's begin with the cylinder heads. And you should be able to see my mouse. There we go. Great. So these cylinder heads, that's this piece here, and this piece down here is the underside, right? These are two large hunks of metal that sit on top of the cylinder heads on the engine block. And like I said, they control the airflow. Let's look here up top, over here, what's going on. So, these bays are where the camshafts will be. We'll talk about those in a second. And you see here, this is where the end of the camshaft would be. It goes through this tunnel here, right? Here's another camshaft. It goes through this tunnel here. And that camshaft is rotating just like the crankshaft. In fact, the core timing of this thing and the way it moves, right, there's a chain, we'll see in a minute, that comes off of the engine and moves up and onto this little gear up here, and that controls the camshafts. And by virtue of the chain, think of like a bicycle. There's where you pedal, and then it moves along the chain to the rear wheel, where it makes the power, right, and spins the wheel. It's very kind of similar kind of mechanism. That's where the camshafts will be. Right now this is a cutaway, so we can see more what's going on here, right? This assembly here is where our headers would mate up. And that's so you can see here there's exhaust that would come out of these 4 holes here. So that's how we start making some of those connections. And then you'll see here there's some tubes up top. Those look like they're related to breathing in some way. It's kind of what you would naturally think. Those are actually where we can put spark plugs in, right? Because the spark plug's going to come in right here. And now we get to the underside. So this is the top end. This is the same cylinder head, just I've flipped it over. And you can see here, each of these 4 areas is where it mates on top of the pistons. And the pistons, as they come up, we'll see the next time in the 4-stroke cycle, they get close to this fascia right here. These little discs here, you see there's 4 of them for each cylinder, those are the actual valves. And as the camshaft spins, it produces pressure on, we'll see soon, these rods, and it opens and closes these valves. These are the valves themselves. You can see here there's 32 of them, because with 8 cylinders, there's 4 valves per cylinder. That's why we have 32. Again, these are accepting the intake, accepting the connections from the intake rudders and the headers, and that is how we're getting airflow in and out of the cylinders. Yep. And it mates to the cylinder deck. There's one thing I forgot here. When you attach the cylinder head onto the top of the engine block, the deck where it meets, metal, like I was saying last time, metal on metal will very rarely hold air. So there's a critical component, the head gasket, which is like a sheet of, it's like a soft material. I'm not sure exactly what it's made of, but it almost feels like cork, like a really thin layer of cork material or rubber or something, right? It's a little bit spongy. And that accepts the connection between the 2 surfaces, and that allows it to be airtight. If you've ever heard the famous phrase, right, I blew a head gasket, right, that's what it means, is that there was a pressure event so catastrophic that it blew that stuffing out, right, between the 2 surfaces, which means you have to fix that, you must go into the engine and remove the heads, which is a very daunting task. That's sort of the major surgery of the car world. So just some trivia there, and let's keep explaining things. Okay, so if those are the heads, the rotating assembly here, and this is a closer view here, this is the cylinder head, and this is where the camshaft would go. This is the actual camshaft, and you can see that we have 4 of them. There are actually 2 camshafts per head, which means we have a total of 4 camshafts to manage. 4 camshafts is quite a few. For example, if you look at I was working on an LS1 block earlier this year. Those only have 1 camshaft, one very large camshaft, but it performs the same role, right? Let's get into the specifics so we can really talk about this. They rotate in time with the crankshaft, and they control the intake valves via lobes. The lobes are these doohickeys right here. You can see how they have a sort of teardrop shape, and as those rotate, they will push the lobes on rockers. And let's see, I don't have rockers here yet, but this all will then connect to the valve springs, which are right here, and then of course the rods and the rockers, right? So these are the rods. So going back here, speaking plainly, this is the underside, right? If I have one of these, and this is the underside, right? So now I'm looking from the top. Here I'm looking from the bottom. Those push through. And so on the other side of this is a spring, right? And the spring has a rocker on top, and attached and touching the rocker is the lobe of the camshaft. I hope that makes sense. What happens is, as those camshafts are moving, the lobes are essentially tapping on these, right? And as they press down on the spring, it pushes that valve down and allows airflow to happen, right, between the different parts of the cylinder. As the cycle continues, this one lets off, and then this one will get hit by the next lobe, right? The exhaust lobe. That's the other thing I should mention. There's the intake camshaft, which controls all the intake valves, and then there's the exhaust camshaft, which controls all the exhaust valves. And there are 2 intake valves and 2 exhaust valves per cylinder. And with the lobes of this moving and pressing on them, it works in this very sort of elaborate clockwork mechanism, which just intrinsically controls the breathing happening at certain rates, right? And the golden rule here is we tend not to want to have the intake and the exhaust valves open at the same time, just like you don't breathe and exhale at the same time. You breathe in, change your valving, breathe out, change your valving, breathe in, right? And it goes on and on and on in perpetuity. And that's how it breathes. The other great thing about these camshafts is because I have a slot for each of them, right? I can have one camshaft moving and acting in a different way from the other camshaft. I can make adjustments to my intake while keeping exhaust the same, and vice versa, or I can move both at the same time, or one. And we'll get into that in a bit. This is a very sophisticated mechanical system, and it wasn't always that we could have 4 camshafts, for God's sake, right? And that they would be able to be adjusted, right? So just to say, we are very spoiled in the current age we live in that we get to have, this level of complexity with these systems. Getting into the other part of the equation here, the angles and the phasers. So looking more here at some anatomy, unique to the S650, the camshafts, which you see now here, are installed. They can be controlled via a set of phasers, and that can set the angles. And so here are the mysterious phasers. So this is a device. It sits here. It's a solenoid, adjusted by a solenoid via the PCM and the ECU. Basically, what a solenoid is like a coil of wire with a rod of metal moving through the middle of it. And if you've ever heard of something in electromagnetic physics called Lenz's law, if I take a current and I run it through that loop of wire, right, that's looped around this piece of metal hundreds of times, the current moving through the wire produces a strong magnetic field. It's orthogonal to the wires, right? It's like it points at a 90-degree angle, and all the force of the magnetic field is moving in one direction, right? So the piece of metal moves from A to B, much like a light switch. And it can either be literally on off, right? Or in the case of a system like this, I can produce a proportional amount of current through the solenoid, and I have a continuum. So like the volume on a speaker, right, or on a radio, I can move very low, very high, medium, all points in between. Really, I can adjust it to whatever level I want at any given moment. These solenoids work in almost the exactly same way. The engine computer has sensors that tell it exactly what position the camshaft is in, and with the phasers, it can say, okay, I want you, the intake, to begin advancing your timing and opening 15 degrees sooner. Exhaust, I want you to also advance, and I want you to open 15 degrees later, right? Technically not advancing, right? The point is I can create a longer breath intake or a longer exhaust intake or shorter, right, by virtue of using these phasers. And that becomes a very big deal because we have to control a variety of different engine conditions for the breathing. There's the idle itself, optimal stability, there's the fuel economy method, right? There's the drivability of partial throttle in everyday traffic, and we don't want our engine to stutter or bog down or not respond when we put the pedal down, right? And that's the other thing, power, right? There's a certain kind of way we want to breathe when we're asking the engine to produce a lot of power suddenly when we mash the pedal. All of that magic happens with the throttle and the drivability by managing these camshafts very carefully. And as we change the engine's breathing, we change its functioning, right? So that's what these phasers do. and you can see how there's a main chain driving this one, and then it controls the timing of the second one, the slave. I don't know which is which. That's maybe your homework. Is this one the exhaust and this is the intake, or vice versa? But anyway, we also have some other interesting functioning here. So again, these are our phasers, and we have something called an intake manifold runner control, and the ECU controls it. The ECU can set the intake manifold runner control to on or off. If it is in the off position, there is less air overall coming into the engine. If the IMRC, intake manifold run control, is set to on, it allows a hell of a lot of air to come in and go out. Basically, you'll see later on, there are a number of driving modes I have, right? And I can effectively double the number of modes I have. Let's say I have 10. And I didn't pick that number randomly. If I have 10 low airflow models, and then with the IMRC turned on, I have 10 more high airflow models, right? This is how I'm, creating the opportunity for these 26 different variable cam schedules. Now, there are times where I might not want that many. And there's reasons why. If I am building a car that I'm going to be taking to the drag strip, I don't need it to have the drivability of everyday street driving. I just don't, right? And in fact, one of the worst things that can happen if I'm trying to produce maximum power at all times is that the engine, for some reason, goes into the lower breathing set of tables, right? That normally the software controls that, but what if something goes wrong? What if my IMRC, for whatever reason, gets broken and is stuck in one position, right? The bottom line is this. There's a way to use lockouts on the phasers here that will prevent it from going into the low IMRC runner position. And I present this just because it's good to know, because there's a lot of discussion on it. You might see as you move from this course to other ventures, right? So the lockouts look like this. This is a cylinder head. These pieces here literally physically lock the phasers in a certain position, so the runners are not going to move. And so those 20 possible schedules that I was moving in, and the other 6 we'll get to later, I've now eliminated a bay of 10 of them. Don't even need to worry about them anymore, right? So that's something you need to be aware of, because later on, you might choose to go down that path. Modifications, things we can do to change our Valvetrain. Okay. So back in the old days, I'll tell a little story here. On carbureted engines, mostly big blocks, if you wanted to produce a big motor, right? And I'll take the example of a stroker motor. If a stroker motor, if you recall in the first chapter 1, I can take a block, I can go into the cylinders, I can increase the length of travel that the piston and rod will go through. Because that length of travel is larger, I now have more airspace in that cylinder. I can change a 5.0 liter engine, for example, to a 5.4 liter engine. That'd be a hell of an adjustment, but go with the example. Okay. If I was to produce that stroker motor and I have all that volume, right, I'm going to have to adjust the breathing that the engine does to be able to fill that volume effectively. So on my camshaft, I may get a camshaft that has larger lobes. Remember those teardrop pieces, right? And so if I was to extend the teardrop to be a taller teardrop or a taller lobe, for example, and also instead of it being sort of like a pointy shape, I could increase the width of that teardrop portion, right? When that shape, as it's rotating, drags over the rocker of the valve, right, and moves through the spring, it'll depress the spring further and for a longer duration, right? And that will then cause more air to enter the engine. Because I have more air coming in, I am producing more power. And if I'm taking real big breaths and I'm opening my exhaust sound a little sooner than usual because I want to get all that air then out after combustion, right? It creates this very characteristic loping sound, right? Because I put a big camshaft in. The phrase hot rod comes from I take out my stock camshaft and I put in a hot rod, right? A large camshaft that's going to cause bigger breathing in this block, right? And that was one of the most fundamental power adders there used to be. This was back before forced induction was a major thing. We'll talk about that later, right? But a larger camshaft is one of the biggest ways you can add power to an engine, along with other modifications. So that's one major valve. Okay, other modifications that I can do. I can port my cylinder heads. So recall I mentioned briefly before, when you attach the cylinder head onto the decking of the engine block, there's a space in there where the intake manifold runners move through the heads and then through the valves and into the cylinder, right? That space in between, when the engine comes out of the factory, it can be rough. It can be narrow by virtue of the fact there's just a lot of metal there still, and there can be little shapes sort of sticking out, and then it's not a smooth surface. A good machinist can go on those heads and that particular little tunnel, right, that kind of has a curve to it, it's almost like sanding, right? They can really take that rough surface, they can make it very, very smooth. They can remove any sort of obstructing shapes. They can understand how the airflow is moving through. There's something called scavenging they worry about, right? And knowing what they're doing, they can make that little tunnel way more efficient, right, to allow much more air to flow much more easily. Think of it like a tonsillectomy. Getting back to the breathing analogy, if your tonsils in your throat are swollen, if it's chronic, it can interfere with your breathing. What happens, right? A doctor will go in, remove those tonsils, and now it's much more easy for me to just breathe through my nose and my throat into my lungs, right? A similar concept, right? We're removing obstructions and we're increasing the efficiency of the airflow. Where I have efficient airflow, I can increase fueling. The two together, I can increase power, right? So this is something that, if you're creating a race car, if your application is racing, it's almost guaranteed that at some point you get your heads ported. For street guys, guys like me who are, I'm not at the drag strip every weekend, right? I'm having fun around town. I'm going, I might go autocrossing, stuff like that. I don't necessarily need to do this, but it's almost taken for granted if it's a true race application. Another element that is similar to that, as I get into advanced engine construction and I understand how my Valvetrain is working, I can go in and adjust my lifters. I can actually change on my lifters from a roller tappet to a flat tappet. And this is the contact point between the lobe on the camshaft and actually the little mechanism where the spring is getting pushed, right? And where the spring's getting pushed, the valve is moving up and down, opening things. So the geometry of this can be adjusted. This is advanced stuff. There's something you have to worry about called valve lashing, which is how tight this arrangement is. There was a point on my tractor, of all things, my Cub Cadet riding lawnmower, where I would turn the key and I would have a very rough start and all kinds of problems were ensuing, and it was sort of getting worse and worse and worse. And one day my tractor just wouldn't turn on at all. Did some research and found out that the valve lash on these things gets out of whack over the course of a season. So open it up, get in there, get to the Valvetrain assembly, which is not that hard, and I used some feeler gauges and found out that the distance on my valves between the lobes and the tappets was too far. So I tightened it up just right, used the feeler gauge to get the depth between them just right, and because it'll pin. The feeler gauge is like it's like a keychain of a whole bunch of metals of different thicknesses and strips, right? And so if you want 0.004, right, and you can put it in there and you feel it grab just right, that's the distance. Wouldn't you know it, my riding mower starts right up. Works great. That's how important these Valvetrains are, right? If something is out of whack we're talking a tenth of an inch is a massive distance for the kind of specificity, right? The machining of these things. So important stuff. And that's right. So the infamous ghost tune. So you remember I was talking about previously on this slide, right? If I put a nice big camshaft in and my breathing is affected and the car has that lop, 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 right? And people know when there's a big cam job, it just sounds awesome, right? You can do something. If you understand the Valvetrain assembly of the S650, you can actually change with the phasers the breathing of the intake and exhaust stroke on these things, such that the intake and the exhaust overlap slightly in just the right way. There's a formula. There's like a magic formula to this. But if you get it, you can produce that loping effect that sounds like you've got a big camshaft, but with this assembly right here. And in a way, it's more impressive than the actual cam, because that's what we're emulating, right? It's a trick. It's a magic trick. The ghost tune is a magic trick. It makes it sound like you've got a big camshaft, like you've got an LSX motor that you built, right? It works because with 4 camshafts, I can mimic those conditions. The very fact that we have the TiVCTs is already far cooler than just having a big camshaft. So I kind of find ghost tunes a little amusing for that reason. But anyway, if you really understand Valvetrain management and you pick up the rest of the concepts in the tuning here, towards the end, I will show you the secret sauce, as it were, to how you would produce a ghost tune, and leave it to you to take that to completion. Okay, next time, and I think this was a little shorter. Next time we're going to get into the 4-stroke cycle and the specifics of it. And we're going to talk about forced induction at a high level, just what it is, right? Spoilers, we're talking turbochargers, superchargers, and how they work. After that, we're going to start getting into the mass airflow model and fueling and fuel trims. We'll also be taking on, following that, the speed density model, the difference between the two. Those are super fundamental, so stay tuned for those. We'll also be talking about open and closed loop. That might get moved into the 2 previous ones. Again, I always reserve the right to move these around in a way that makes sense. Then we're going to be looking at the HDFX, and that is extremely relevant to what we looked at today, because I talked about the 26 variable cam schedules. We're going to be looking at something called mapped points, and we're going to be understanding how the ECU moves between those mapped points to adjust and accommodate different driving conditions. So that's really going to be, and that is very S650 specific. That's going to be very compelling stuff, right, that we want to understand. And I would venture to say, I know I'm very long-winded in these presentations putting together, but it's all building up to that HDFX portion, right, and how we move through the schedules. That is not something you're going to find in other books. It's not something you're going to find on forums. This is stuff that I had to really painstakingly go seek out and find, and ultimately talk to other tuners in some private messaging for them to shed some light on this. So I will share with you what I discovered. That's the good stuff. Then we're going to get into the practicality of tuning the S650, and that is where I'm going to introduce the core workflow of the steps we're going to take for a basic tune, and we're going to get into math calibration. If you can't wait for that, that will be a detailed sort of hand-holding exercise. I'll be showing you specifically in the software exactly how to do this now that we've gone through some of the theory here. If you can't wait, I did produce a quick and dirty MAF calibration video. It's meant like one tuner to another. Check it out. But if you're coming to this series late, and I've already finished a whole bunch of these other tutorials, then you can go ahead and head over to that MAF one. If, again, you're also I just can't wait, I just want to see. But the thing is, like I was saying, theory and praxis. If you just go there and you just mimic what I'm doing with the software and you don't understand why it is what I'm doing, you're just going to run into problems, and then you won't be able to solve them. That's why it's important to know these concepts. So that, I think, is it for today. Thanks a lot. See you next time, and happy tuning.